So, just some quick announcements. Worksheets 8 through 12 will be due on October 7th. Homework number 2 will be also due on October 7th. The test grades will be up later today. They're already graded. I just need to finish the curve. And I was hearing some things that sounded like people were having some confusion about worksheets and homework assignments. If you go here, I will pretend to be a student. So this is what the bright page looks like as a student. If you go to content, homework and worksheets, here you'll see the first set of worksheets, 2 through 7. They're all quizzes. They're all overdue, as you can see. Homework number 1, which is the various problems from your book, it's an assignment. And then the second set of worksheets, 8 through 12, and homework number 2, problems from your book. So for the homeworks, these are assignments. You do the problems in your book, and then you can submit a file of the write-up. Or at the due date, you can turn it in on paper. Oh, I don't need to do that. Just need to stop being a student. Yeah, and as I mentioned, the test grades will be up later today. I'm just working on the curve a bit. Because looks like maybe I miscalculated running the test, so I'm correcting it with a curve. But yeah. Remember, you get a sheet of notes for tests. So, continuing on our discussion, large impacts. So large impacts are, we've been talking about the Earth and the Moon. The Moon has lots of craters on it from impacts. Large impacts are when something big impacts. I mean, there's lots of impacts of various size, but large impacts can have a large effect on the Moon or on Earth. Again, the most dramatic historically was probably the one that took out the dinosaurs. And it is, let me see if I can look up how to pronounce that. Oh. You know what? No, I don't have any chance of pronouncing that. It's got an X in it, and so there are about 190 confirmed craters bigger than 100 meters across on Earth. Earth doesn't actually have a lot of craters because Earth has an active geology that erases those craters. So things like erosional processes and geological processes cause craters to get destroyed because, movement of water and wind and such will erode things down. Sediment can deposit on top of craters, things like that. Additionally, Earth has a not insignificant atmosphere. So small objects never make it through the atmosphere. They burn up on the way in effectively, and they can explode sometimes, which is dramatic, but they never actually make it through the atmosphere. And then lastly, most of the surface of Earth is water. And when things hit the water, they don't leave craters. They splash. So how often do impacts happen? Well, small meteorites hit the atmosphere constantly, every day. They burn up in the atmosphere every day. And over decades, meteorites will eventually strike the Earth and do some damage. In general, damage that's been in recorded history for meteorites has been mostly small amounts of property damage. Literally one person has ever been recorded being hit by a meteor. All right. I think she broke her hip, but like literally one. And then there was a whole mess with that. The following legal complications of it were depressing and dumb, but yes. Over tens of thousands of years, a major impact will cause localized devastation. I mean, the biggest one of these recently was probably the biggest impact that caused significant damage recently was something like the Tunguska event, which airburst. That's hundreds of years. But over tens of thousands of years, you can get localized devastation, kind of like the impact that created Meteor Crater. And then over hundreds of millions of years, you can get impacts so potent that they cause extinction level events. Like the impact that took out the dinosaurs, which maybe I can find a pronunciation for it. I had it over. Maybe this will read it for me. The Chico, I have no idea how to pronounce the X in it. Sorry. So the Tunguska event was in Siberia in 1908. The object never made it out to the surface, actually. It exploded about 5 miles above the surface. It didn't leave behind a crater, but it flattened 1,000 square kilometers of forest, was heard for hundreds of miles, and did some minor damage. So that was probably the biggest recent event. Now, mass extinctions happen every once in a while. There's been about 5 in the last 500 million years, where most, we have these massive dips in well-defined genera, mass die-offs of living things. And the most recent of these was about 65 million years ago. This is the one that took out the dinosaurs. And there's evidence of a crater off the Yucatan Peninsula, and there's an iridium layer in the crust dating to this time. So these yellow triangles are the big 5 mass extinctions, and there's some other smaller mass extinctions as well in between. This peak here where things are going up, that's just because it's easier to identify more recent things. This has the general curve has more to do with the but it's a look up. It has some of it has to do with like what survives as fossils. But there's been about 5 mass extinctions. I think only one of them was actually due to a massive impact. Most they've had various different causes. So some are due to massive geological events. The 165 million years ago was an impact. There's an iridium layer in the crust that dates to this time as well. Will future impacts occur? Yes. Probability allows us to estimate how often these will happen, but not when. would be a year from now, a decade, a century, a millennium, or longer. And there are thousands of objects that are known to cross Earth orbit. The problem is that they're small, dark, and difficult to detect. And once you have identified them, it's still hard to predict if they're ever going to hit Earth, because every time they get close to Earth, that perturbs their orbit, which makes small differences, like tiny differences in their orbit that are hard to measure, lead to big changes in the chance of whether they're going to hit something. So there's a lot more we've yet to detect. There are people working on this seriously. So the Earth has been impacted by objects from space in the past. Larger objects impact less frequently, and massive impacts can cause significant damage, including extinctions, the most dramatic of which is the event that caused the extinction of the dinosaurs and left behind the KTV. Let's skip past that announcements page. So, phases of the moon and the tides. Let's talk about those. So, the lunar phases are caused by the shadow of the moon on itself. Half the moon is illuminated by the sun, because it's the side that's facing the sun. The other half is in shadow. And half the moon is always visible from Earth. In fact, it's the same side of the moon, always. Because the moon's rotation rate and its rate of revolution around Earth are the same. So when we look out, we always see the same side of the moon, the near side of the moon. And that side of the moon has a different amount of illumination depending on its travel around the Earth. So if the side of the moon that we see is also the side that's facing the sun, we get a full moon. As the side of the moon we see, as the moon moves around, we get less and less moon visible from Earth. Again, it's always half the moon is always illuminated, but what we can see from Earth changes. And eventually, the side of the moon is on the same side of the Earth as the sun. So the side that's illuminated is the far side of the moon, and we get a new moon. And then the size of the moon increases during the waxing phase. So the phases are described. You talk about there are waxing phases and waning phases. Waxing means getting bigger. Waning means getting smaller. So waxing phases are when there's more illuminated each day. Start at the new moon, going to the full moon. Waning phases, there's less illuminated each day. Starting at the full moon, going to the new moon. And the phases traditionally start from new. They're if the moon is less than half illuminated, it's called the crescent moon. So you go new moon, waxing crescent, first quarter when the moon is half illuminated, because it's a quarter of the way around. Waxing gibbous, gibbous moon is more than halfway illuminated. Full moon, waning gibbous, third quarter, because it's 3/4 of the way around, and then waning crescent. So the lunar phase cycle, the cycle of phases is called the synodic month. It is 29.5 days long. But if you look at the time it takes the moon to move once across the background of stars, so the actual time of revolution of the moon, that is 27.3 days. And the sidereal month is shorter than the synodic month for the same reason that the sidereal day is shorter than the solar day. it takes a little bit longer for the moon to catch up with the sun again. But because it moves more slowly, it's a couple days instead of 4 minutes. So the phases go new, crescent, quarter, gibbous, full, gibbous, quarter, crescent, new. You can see this pattern right here. You know, you start with a new moon where you can't see the moon, you get a sliver of moon and it builds up till it's halfway illuminated. Apparently that was a cloudy night. The gibbous moon, the full moon is here, I believe. And then the other half is illuminated and it cuts out to a crescent and you get another new moon. So during the waxing phase, you see one side of the moon. During the waning phase, you see the other side of the moon. So the phases depend on the position of the sun and the moon. The new moon is when the moon is in the same direction as the sun, so it rises and sets with the sun. So you'll notice over the period of a month, the moon will be closer to or further away from the sun in the sky. It'll be furthest from the sun at a full moon, which is often why you get, or near the full moon, you can get that fun situation where the sun is setting on one side of the sky and the moon is rising on the other. So the new moon is always in the same direction as the sun. The crescent phase will always be close to the sun in the sky. The quarter phase will be halfway across the sky from the sun. The gibbous phase will be more than halfway across the sky to the sun. And the full phase will be opposite the sun in the sky. It will rise and set opposite the sun. The rotation and revolution of the moon are exactly the same. So always one side of the moon is facing us. So there's a near side of the moon, which is the side that we see. And interestingly, most of the Maria, those dark areas on the moon, are actually on the near side. The far side is actually much more mountainous and lighter in color. So half the moon is never visible from the Earth. It wasn't seen until 1959 when the Luna 3 probe orbited the moon and was able to take pictures from the far side. And it's not really a dark side of the moon. All of the moon gets 2 weeks of sun every month. It has effectively a day-night cycle where the day is 2 weeks and the night is 2 weeks. But yeah, so all the moon gets the same amount of sunlight over the month, but it is a far side of the moon, the side we can't see. Now, one of the effects of the moon is tides. So gravity depends on how far you are from the object that's pulling on you with gravity. The further apart you are, the weaker gravity is. And it turns out, if you have some size, like the Earth, that means there's a difference in gravity on one side of an object compared to the other side of the object. So tides are caused by both the moon and the sun, and it's due to this differential gravitational force. So if we look at the gravity from the moon, if this circle is the Earth, the near side of the Earth is pulled stronger than the middle of the Earth, which is pulled stronger than the far side of the Earth. And if you subtract what the middle of the Earth is being pulled by, because everything is being sort of pulled together, what this effectively does is creates an apparent force going out towards and away from that object. Basically, you're being stretched. So the gravitational force depends on the distance. The near side of the Earth is closer to the moon, so it gets a stronger force. And the reason we see tides with water because this differential force, this effect, this tidal force that effectively pushes stuff on either side of the Earth, towards and opposite the moon, away from the center, it affects everything. But we see it with water because water moves more easily than rock. Water flows better than solid rock. This gives us tides. The most dramatic tides have to do with more. It's not that the moon is pulling so hard that you get really huge tides in certain places. It's that as the water moves sideways, it gets funneled into certain places and it piles up really high. So the biggest tides in the world have to do with the geography that funnels the tide water into a place. But tides affect, tidal forces like this affect all kinds of stuff. Anything that's being affected by gravity has tidal forces. And we experience tides from both the moon and the sun. The moon's tides are bigger because the difference in distance is a bigger effect from the moon than from the sun, because we're so much closer to the moon. So the size of the Earth compared to the distance of the moon is a bigger change. Sun's gravity is much stronger, but the change due to the distance, we're so much further from the sun. So the tides from the sun are about half that of the moon. So what they effectively do, the tides from the sun effectively just adjust the tides from the moon. So the sun also produces a tidal force on the Earth. It's about half that of the moon. And what this does is that when the sun and the moon line up, tides get bigger. And when the sun and the moon are 90 degrees apart, as you can see here, tides get smaller. So at the new and the full moon, the forces work together to produce bigger, stronger, what are called spring tides, because they spring up. And at the first and third quarter, the forces work against each other to produce weaker neap tides. So that's part of why the tides will change during the month. And if you look at like this set of tide tables, you can see how they would change. We don't see huge tides here because Lake Michigan's not that big. You see bigger effects in the ocean, but there are tides. They can be observed. So the phases of the moon depend on the position of the sun and the moon. Specific phases are visible at specific times of day, and the tides are caused by the differential pull of the moon and the sun on the Earth, and water moves in response to the excess force. And these tidal forces, this stretching caused by differential gravity, has a lot of effects elsewhere in the solar system. Turns out a number of the moons of the gas giants are heated by tidal forces. It's a little different than what's going on with Earth and the moon, but basically they have elliptical orbits, so the tidal force changes over the orbit, and that effectively squeezes and stretches them during their orbit, and that heats them up. So tides, they're due to the gravitational force on the Earth from the moon. The force on the near side of the Earth is greater than the force on the far side. And we see it with water because water flows. The sun also has less effect, but it does modify the lunar tides. So if you want to look this up in your textbook, it's in chapter 4.6, all the details about tides. And tides tend to exert a drag force on the Earth. Additionally, they slow its rotation, and this will continue until the Earth rotates synchronously with the moon, so that the same side of the Earth always points towards the moon. Well, theoretically, it will continue until that point. In actuality, the Earth will be destroyed before it reaches that point by other factors. But the Earth is slowing down because of the tidal forces of the moon. And in that process, also, the moon is, there's an effect on the moon as well. And so the moon is actually changing position. And this has already happened with the moon. This process has continued to the point with the moon. The tides from the Earth have slowed down the moon enough that the same side of the moon always faces the Earth. And this happens with other objects as well. Lots of the moons of the large planets are tidally locked, so the same side always faces the planet. The most dramatic pair of tidally locked objects that we've covered is probably Pluto and Charon. They're tidally locked to each other, so they always have the same side facing each other. Yeah. So now let's talk about another dramatic thing involving shadows in the moon, which is eclipses. There was a lunar eclipse a little while ago, but it wasn't visible on this continent, so I didn't really bring it up. I think it was weekend before last or something. So, how do we get eclipses? Well, it turns out that we happen to live at a time when the moon and the sun are about the same apparent size as seen from the Earth. This is actually like kind of neat. So they're about 30 arc minutes or half a degree across. This was not true in the past. The moon used to be closer to the Earth, and it will not be true in the future. The moon is actually steadily moving away from the Earth. But we happen to live at a time when the moon is just about the same size as the sun, which gives us the best solar eclipses in the solar system. Because we can get dramatic things like this happen. So a solar eclipse is when the moon passes in front of the sun. When something passes in front of the sun, that is a solar eclipse. If you'd like to see what solar eclipses look like on every planet, there is a tool from Minute Labs that has animations of them all. And you can see that we have the best. Because our moon and the sun are just about the same size. Most other planets, they're either too small or too big. And even when they're roughly around the same size, they're often too far away. The sun is much less impressive in the sky. Because the other planets that have big moons are also much further away from the sun. The sun is much smaller than the sky. So this is a solar eclipse. The moon passes in front of the sun. There's usually about 2 of these a year, but where they're only visible in a small area on Earth, and so you have to be in the right place. So the next one that hits the US is not going to be for quite a while. There was a big one recently, a few years ago, that was quite nice. And then a lunar eclipse is when the moon passes into the Earth's shadow. These are much easier to see. About half the Earth can see them. If it's nighttime when it happens, you can see it. The most recent one, unfortunately, we fell into the small portion of Earth that couldn't see it. But these are also called blood moons. You've heard of something called a blood moon? Because during a total lunar eclipse, the moon turns red. Because the only light illuminating it is red light that gets bent around the Earth. And so it's called a blood moon. So here's the geometry of an eclipse. This is a lunar eclipse. You have the sun, something that is throwing a shadow, and something passing through the shadow. So the shadow has two parts. The darkest complete shadow portion is called the umbra. This is where the sunlight is completely blocked. If you are in the umbra, you see a total eclipse. So if you see a total eclipse of the sun, you're in the umbra from the shadow of the moon. Surrounding that is the penumbra, which is a region of partial shadow. The sunlight is partially blocked. And if you're in the penumbra of a solar eclipse, you see a partial eclipse, you see the sun partially covered. That recent eclipse, I guess it was 2024. We were able to, from Chicago, to see like 95% coverage. So this is a lunar eclipse. You can see the moon is passing through the shadow of Earth. Earth is bigger than the moon, so its shadow is subsequently bigger, and more of Earth can see the moon when it passes into the shadow. But the shadow of the moon on the Earth, only a small area of the Earth is actually in the shadow of the moon, and so it lasts much less time because the moon is smaller, and so subsequently the shadow is much smaller. So a total solar eclipse, that's when you're in the umbra. That is when the entire face of the sun is blocked. Looks like this. A partial solar eclipse is when part of the face of the sun is blocked. If you're in a place that will get totality, you'll see a partial solar eclipse until the sun completely covers up, until the moon completely covers up the sun, and then you'll see a total solar eclipse. And then it'll go partial. What you see when you're not quite there is that the moon will move across the sun and not quite completely cover it. It will miss, it's slightly misaligned. And then sometimes you'll get an angular solar eclipse. The eclipse that was immediately before the recent total solar eclipse in the US, which I think was in fall 2023, was an annular solar eclipse because it was spring 2024 and fall 2023, where because of the orbit of the Earth around the sun, the Earth was a little closer to the sun. The moon was a little further away. You get an angular solar eclipse. The moon wasn't quite big enough in the sky to completely cover the sun, and you get a ring of sunlight visible around the moon. This is when the moon was a little bit more distant and maybe the sun was a little closer. I think both of those were the case. But this will eventually be the only type of eclipse that happens as the moon moves further away from the Earth. Now, lunar eclipses occur when the moon passes into the shadow of the Earth. A total lunar eclipse is when the entire moon is in the umbra of the Earth and it goes red, called the blood moon sometimes. A partial lunar eclipse is when part of the moon is in the umbra of the Earth. And these were actually used by Aristotle to show that the Earth was round, because the shadow the Earth threw on the moon was round. And then lastly, a penumbral lunar eclipse is when the moon passes only through the penumbra of Earth's shadow. And these are basically invisible to the human eye. The change in the brightness of the moon is so small that you need dedicated instruments to detect it. So, I mean, it only drops by like 5% brightness or something. So here is a short video about eclipses and how they work.
Hello there and welcome back for another Smart Figure. After watching this video, you should be able to distinguish between the two kinds of eclipses, solar and lunar. Here are a series of photos showing the development of a solar eclipse. the maximum solar eclipse where the sun is blotted out by the moon, and then the decline of the eclipse again back towards a normal look at the sun. A solar eclipse is when the sun is eclipsed by the moon. And what this means is that the moon moves between Earth and the sun. And so the shadow of the moon is projected onto the Earth's surface. The path of the total solar eclipse is where we have what's called the umbra, basically the maximum shadow, nothing but shadow, and the size of the moon is almost about the same size as the sun. And so we basically see a black circle in the sky, and then that's surrounded by emanating rays of the sun. There's a wider area surrounding the umbra called the penumbra, and that's where there is going to be a partial solar eclipse. So if you're standing in the penumbra zone, you will see the sun partially obscured by the moon. Now there's also a lunar eclipse, and this is when the moon is eclipsed. Rather than the moon getting in between the Earth and the sun, the Earth is getting in between the sun and the moon. And so the shadow of the Earth is actually cast onto the moon itself, again with this sort of umbra-penumbra relationship. And that puts the moon in shadow. Now, this is not by any means the same thing as the phases of the moon, where we see a new moon, a waxing crescent moon, a first quarter moon, a gibbous moon that's waxing, and so on. Here, what we're seeing is something that transpires in a matter of hours where the moon passes through Earth's shadow. The regular phases of the moon are caused by the moon's own shadow, but this is the Earth's shadow instead. You can see that the boundary between shadow and not shadow is much more diffuse than in the case of the phases of the moon. That's one way to tell the two apart. Okay, quick quiz here. See if you can spot whether this is a solar eclipse or a lunar eclipse and tell me why. All right, so the sun's on the left, and then we've got the two objects on the right, one of which is the moon and one is the Earth. Obviously, the Earth is the bigger of the two. Here, the moon is between the Earth and the sun, and the moon is casting its shadow on the Earth. So this would be an example where the people in the umbra are basically going to not be able to see the sun. The moon's going to be blocking their view of the sun. So the sun will be eclipsed. Therefore, this is a solar, not a lunar eclipse. Thanks a lot for your attention. This has been another Smart Figure.
But yeah. So we can predict eclipses. People have been able to predict eclipses for thousands of years. In fact, you may have heard of the Antikythera mechanism, and another word I can't pronounce. The Antikythera mechanism, which is this calculating device found in a shipwreck, ancient Greek shipwreck. It's from about 100 AD. One of the things it did was predict eclipses. Yeah. And it's impressive because it's very early clockwork. But eclipses don't occur every month. And this is actually because the moon's orbit with respect to the Earth's orbit, the moon's orbit around the Earth compared to the Earth's orbit around the sun is tilted by about 5 degrees. So there's actually only about twice a year that you get an eclipse season. So we're currently in eclipse season. There was a lunar eclipse on the 7th. There will be a partial solar eclipse on the 21st, visible from like New Zealand. And there are 2 regions when the orbit of the moon lines up with the orbit of, when the moon in its orbit is not too high or too low, compared to the orbit of the Earth and the path of the sun. And those create eclipse seasons. They both last about a month. You have a descending node and an ascending node. So you usually get 1 solar and 1 lunar in each eclipse season. And because this is all just due to orbital mechanics, eclipses can be predicted. There's a cycle called the Saros cycle, where eclipses each individual eclipse effectively repeats every 18 years, 11 days, and 8 hours. But because of that 8 hours, it moves about a third of the way around the Earth. So these patterns all repeat. And that means you can look up all the eclipses for the next couple of centuries on Wikipedia. There's just big tables of them that show exactly when the next eclipse is. So the next eclipse that's coming up, there was going to be a partial solar eclipse on the 21st that's visible from New Zealand. There was a lunar eclipse on the 7th that was only visible from basically the other hemisphere. So Europe, Africa, that side of the planet. And then so usually at the moment they happen, one node is in the fall and one node is in the spring. So they do slowly shift throughout the year. But we can actually, predict how that happens. So currently the eclipse seasons are like September and April. And I think they're slowly moving into August and May. So when you observe an eclipse, for a lunar eclipse, you don't need anything special. It's just the moon. You can look at the moon. It's safe to look at the moon. But for a solar eclipse, it's never safe to look at the surface of the sun. That is a good way to seriously damage your eyes. I assume you like having functional eyes, so I would not suggest doing that. But there are a couple ways that you can safely look at the sun. You can use a pinhole camera, which is what they do in solar observatories, basically, where instead of looking at the sun, you project an image of the sun onto another surface and look at that. And you can use solar filters, which are incredibly dark filters that block out the vast majority of light. And don't use like welding goggles because they aren't dark enough. Solar filters are like significantly darker than welding goggles or other things to protect your eyes, because the sun is in fact much brighter than a welding arc. But if you're in the path of totality, you can actually look directly at a total eclipse. That's safe to view because the sun is all blocked out. But you need to be careful and need to know exactly when the eclipse starts and ends. These days there are apps for that, so it's not that difficult. But like the totality of an eclipse, the total portion of an eclipse only lasts for a few minutes. So you'd only have a few minutes. I don't know why I repeated that slide. I must have had pictures and they're gone. So these are some previous eclipses. With some weird editing. So there was a dramatic one on April 8th, 2024. There was an annular solar eclipse on October 14th, 2023. Those were the ones that were visible in the US. These are the paths of those eclipses. The next one that's visible in the US is in like the 2040s, I think. I don't know. It's a while. So these are animations showing those eclipses and how they're going to go across the Earth. And you can see these. I just got these off Wikipedia. So if you want to see any of the upcoming previous eclipses, you can check. And yes, they have tables that go for the next couple of centuries. So the recent eclipse on April 8th 2024 was a big deal because this is an eclipse that passed over the most, where totality passed over the most among the largest number of people. It covered a lot of area over land, and it covered a lot of area with a lot of people in it, because it went over the eastern half of the US, which is pretty densely populated. So this is like on record, one of the largest number of people were able to see this directly. So here's a video about this, showing the various things we tracking it and images of it.
Welcome to live coverage of the celestial event of the year, the total solar eclipse. Today, NASA and the Great Lakes Science Center is hosting this free outdoor event for the community to experience the total solar eclipse. We will follow the moon's shadow as it races across North America.
We're live from the Kerrville Eclipse Festival.
We are at the Indianapolis Motor Speedway. Things are looking absolutely fabulous.
We are here at Niagara Falls.
Crowds are filing into the stadium.
The solar corona is going to look very cool today. It's going to look cooler than it did last time.
You guys ready for an eclipse?
Here we go! Look at that. Fantastic. Oh my God, it's gorgeous. Oh my gosh.
I think we're very fortunate to be here at this special vantage point to see such a special event.
Oh my gosh, that is
Gorgeous.
And for more NASA videos, hit subscribe.
And while I did not manage to see totality, because I unfortunately had to work, so I couldn't drive a couple hours downstate. It was very interesting to watch it throughout the day. And we got enough coverage that it was dramatic. So. And then here is a time lapse of that eclipse up to totality. So you can see the moon is steadily covering up the sun. This is from Mazatlan, Mexico. And this is totality. So, the general idea of eclipses, they're when the shadow of one object falls on another. A solar eclipse is when the moon passes in front of the sun and blocks it out. A lunar eclipse is when the moon passes into Earth's shadow. They don't occur every month, but there are predictable patterns. There's generally about 2 a year, because there is an eclipse season when the orbit of the moon and the orbit of the Earth line up so that at the new and full moon, the moon is lined up with the orbit of the Earth. And so that happens about twice a year, lasts for about a month, and we get about 2 eclipses of each type per year. So you generally get a solar and a lunar, and a solar in the ascending node, and a solar and the lunar in the descending node. They're called the ascending node and the descending node, and Remind myself which one. So the descending node is the one in the fall. The ascending mode is the one in the spring. So let's talk about the structure of the moon. The moon has a mass of about 0.0123 Earth masses. It's about 1.2% of the mass of the moon, and its diameter is about 27% that of the Earth. Its surface gravity is only about 17% of Earth's gravity. It's about a sixth of Earth's gravity, and it is less dense than the Earth. So the Earth is about 5.5 grams per cubic centimeter on average. The moon is only 3.3 grams per cubic centimeter. And its rotation period is 27.3 days. And it orbits around the Earth in the same amount of time. So, some of the exploration of the moon. So the moon is quite regularly explored. In 1959, Luna 3 had the first view of the far side of the moon. This was the Luna missions were all by the Russians. And then in 1966, Luna 9 had the first soft landing on the surface of the moon. I guess I don't have a picture. 1969 through 1972 were the Apollo landings, where we actually sent humans up to the moon. What? What? You were first. The US sent humans up to the moon. Well, the Russians weren't actually trying very hard, it turns out. There was a lot of weird politics going on both sides. But the Apollo landings, we sent humans up to the moon, landed on the moon. A lot of information was recovered from these trips. And most importantly, we brought back a lot of rock samples. So there's been the biggest source of moon rocks has been the Apollo landings. I believe there's been a couple other landers that have landed on the moon and sent back samples on like a rocket that were like automated, remote landers. There was one by the Russians and one, I think, by the Chinese, but both sent back very small amounts. While the vast majority of samples of moon material were brought back on the Apollo missions. Because, the Apollo missions brought back boxes of the stuff. These other missions brought back like 100 grams. So in 2009, we got the Lunar Reconnaissance Orbiter, which is constantly orbiting the moon and taking images. So here we have images of one of the Apollo landing sites. There's been a couple of interesting things where like they were able to see new craters where they passed over a place and then went back over it and there was now a crater after people had seen an impact. And then in 2013, there was U2, which was a lunar rover not sent by the US. So it's actually the start, other people actually managing to get, I think that's the Chinese one, the Chinese lunar rover. So the composition of the moon. It's primarily made of rock. It has significantly less metals than the Earth does. It has no atmosphere. Its gravity isn't strong enough to hold on to an atmosphere. And there's water ice detected in some craters. So there is water on the moon. We found water ice in craters generally near the poles that are in permanent shadow. But there is no real atmosphere of it. Now the regions of the moon. There are dark colored regions. These are called maria. They have few impact craters, so they're younger surfaces. And then there are more rugged, lighter colored regions called the highlands. They have lots of impact craters, as you can see here. It's believed the maria were created by really big impacts that caused the crust beneath them to basically crack, and then these craters flooded with lava. So the rocks found in maria are basalts. They're dark covered volcanic rocks. They're vesicular. They have lots of trapped air bubbles. They're the kind of things you see out of these flood lavas. Because there's places on Earth that basically have flood lavas like this. It's very similar to the kind of rock you get from volcanoes like in Iceland or in Hawaii or other places where there are flood basalts. So it's thought that the maria were these big craters. There was they're all more or less round. Massive impact, it cracked to the ground underneath, and they flooded with lava. And then there's lighter colored volcanic rocks that are at north-to-site. These are a lower density rock. These are more common in the highlands. And then there are brachial. These are created by impacts, where material knocked loose from impacts melt and fuse to form a new rock. Now, there are erosional processes on the moon, but they're very different than they are on Earth. Because the primary drivers of erosion on Earth are wind and water. There's no wind and there's no water on the moon. But it does get hit by stuff all the time. And in fact, it's constantly hit by micrometeorites. So the main way that things get worn down and worn away on the moon are micrometeorite impacts or other meteorite impacts. And that means that the surface of the moon is covered with debris from meteor impacts. It's called regolith. Regolith is the technical geologic term for soil without any organic matter in it. So it's lunar regolith. It's basically this powdered soil on the moon. It has a unique structure. It's very long and spiky because of the way it's generated by being melting and splashing from impacts and things. It means that it has a lot of empty space in it, so it can compress, which is why the astronauts left such nice clear footprints. So if you take lunar regolith, which we have a bunch of because the astronauts decided there was space left in the box, so they just shoveled a bunch of dust in, which was brilliant, it turns out, and was incredibly useful. But we've actually been able to make like artificial lunar rock because of this, our understanding of this. And it like put a footprint in it and it just stays because there's so much empty space that when it compresses, it like locks up tighter. But apparently this stuff was awful. It got everywhere. It smelled like gunpowder. It was just kind of nasty. And it probably wasn't very good for their health. Because spiky things that get into your lungs are bad. So the moon is our closest neighbor, but it's quite different from the Earth. It has two distinct regions, the maria and the highlands, and different types of rocks have formed on the moon over its history. So the moon has these large dark areas called maria. They're called maria because early observers thought they were oceans because they were dark. They look kind of like bodies of water if you're not seeing them very clearly, because they were darker than the lighter areas. Maria means sea in Latin. And they're due to lava flow. So they're much flatter. They don't have many other impacts because they're much younger surfaces. Now the far side of the moon, interestingly, is heavily cratered, but has very few maria. So it's thought that most of those impacts happened on one side, and then that side ended up being the one that was facing the Earth. And so the moon is covered in craters. These form when a meteoroid strikes the moon, an explosion ejects material, and it leaves behind a crater. And if that impact is big enough, it can crack the crust enough. Earlier in the moon's history, it could crack the crust enough that magma would flow up through the cracks and flood it with lava. So craters are typically about 10 times as wide as the meteoroid that creates them, and about twice as deep. And the rock gets pulverized to a much greater depth. And most lunar craters date to at least 3.9 billion years ago. There's been a lot less bombardment since then. Basically, most of the impacts happened in the early solar system when there was a lot more junk floating around. But as that junk hit stuff, it got used up. So the rate of impact dropped throughout the solar system. So here are some examples of some very large. Here's a very large lunar crater. And here is a very small lunar crater on this droplet. It was brought back from the moon. And this is 5 centimeters across, 50 millimeters. So this is like a centimeter ball, and this is a microscope shot of it. So it's a really tiny. So yeah, that sphere is a couple centimeters across. It's like this big, and then it's got a tiny impact crater on it. So the thick layer of dust that was left by meteorite impacts is called the regolith. And the moon is still being bombarded by very small micrometeoroids that slowly erodes and softens features. So this is, you can see the dust here in some of these images from the moon. And they've been collecting rocks and stuff. So craters happen somewhat regularly. And there's basically several types of craters that we can observe on Earth. And just in general, you can have volcanic craters, like Crater Lake here. This is the top of a volcano that, after it used up all its magma, the magma chamber collapsed, left behind this caldera, which turned into a lake. There's still a little bit of activity, which is why there's a little volcano here in the middle of Crater Lake. It's called Wizard Island. But you can also have, so that's a volcanic crater. This is a crater caused by a volcano. But you can also have craters caused by impacts. This is meteor crater. So there was a chat. This is meteor crater in Arizona. It's one of the best preserved impact craters on the Earth because it's in a desert and it's relatively young. It's only 50,000 years old. On Earth, we find a lot more volcanic craters and a lot fewer impact craters. And it's the other way around on the moon. On the moon, we find lots of impact craters and only a few volcanic structures. There are some volcanoes on the moon. None of them are active, but there are some. Go away. So the way that craters are created, some object will strike the surface, causing an impact, and material will get thrown out of the crater. This is caused with a shock wave from the impact. So you have contact and compression, and then excavation. Then the material collapses back onto the sides of the crater. So the edges of the crater can fold over. The center will bounce back up because it gets compressed by the shock wave from the impact. And then it will relax back up. So material will collapse back in the crater. And then eventually the weathering can affect, the weathering effects will modify the crater. The diameter is generally about 10 times the size of the object. The depth is about 2 times the size of the object. You can think of this like this hits the ground so hard it causes the ground to splash. So a crater is sort of like a splash in rock or in the ground. And some things you get from an impact crater. You get an ejecta blanket, which is material thrown outwards from the impact crater onto the surrounding area. So here we have an impact crater, and you can see the sort of blanket of ejecta going out in all directions from it. You can also get crater rays, which are long, thin lines of ejecta that extend out to long distances. And sometimes you can also get secondary craters where pieces of debris create smaller craters around the primary impact site. So how do we determine the age of impacts? Well, the craters on top are younger than the craters on the bottom. So craters formed on top of another crater have to be younger, because the bottom crater was there when the first crater happened. Fewer craters implies a younger surface, but to find the actual age of some surface, you need a sample to do radioactive dating. And radioactive dating uses various radioactive minerals in the rock to determine the age. So if the cratering rates on the moon were constant and the same as they are today, that would imply the highlands are older than the universe. This is clearly not the case. The moon is not older than the universe. What that means is the cratering rates haven't been constant over time. There were a lot more impacts early in the history of the solar system and less later. Basically, the way I think about it is that the stuff that was doing impacts steadily gets used up. Because a lot of the time, what causes the impact doesn't survive. Or, it hits something, it's gone now. It's not flying around to run into something anymore. I mean, you can get stuff ejected from an impact that can land somewhere else, which is why we have a few meteorites on Earth that are from the moon and Mars, where really massive impacts knocked material from those that eventually made it to Earth. But in general, cratering rates have been relatively consistent throughout the area of the solar system, which means we can compare crater counts for objects near the center of the solar system to objects far from the center of the solar system, things like that. So we can compare the relative ages of widely separated objects. They varied through time, but they were about the same sort of space. So they're both volcanic and impact craters. Impact craters are created when an object strikes a surface and explodes. And the number of craters on a surface can tell us about the relative age of the surface. So let's talk about the origin of the moon. So the moon is weirdly big for its place in the solar system and compared to the planet it's orbiting. If we look at the other terrestrial planets, the only one that has moons is Mars, and they're tiny. The moon is, among the biggest moons in the solar system. It's like number 5, 6, something like that. Up there with the biggest moons of things like Jupiter and Saturn. But the Earth is tiny compared to Jupiter and Saturn. So there's been several theories throughout history of how the moon formed. So one of the theories is what's called the fission theory, where the Earth spun fast enough that part of it was flung off and formed the moon. But how could the Earth have spun fast enough for that to happen? We don't have a mechanism to explain them. Another is the sister theory, where they formed at the same time, where basically, as the Earth formed, the moon also formed. They were sort of partners. But then why is the composition of the moon different from the composition of Earth? Then there's a capture theory. How could the Earth have captured the moon? It's so big, we need to lose a huge amount of energy to be captured. And we don't have a good explanation for that. So the current accepted model for the origin of the moon is called the giant impact hypothesis, which has the added advantage of having a much cooler name than the previous theories. Not that that has any actual impact on whether or not it's true, but this is our best model for understanding how the moon formed. So the thought is that actually a large Mars-sized object struck the Earth, slammed into the Earth in the early history of the solar system. This disrupted the Earth and flung a large amount of material out from the Earth, but mostly from the upper layers of the Earth and this Mars-sized object. Thus, the lighter layers, leading to a lighter moon. And then a lot of this material got lost, but some of it condensed and formed the moon. And we can run simulations of this, of something about the size of Mars slamming into Earth and flinging material outwards, and it produces basically our moon. This explains certain properties of the moon. The Earth has a high density, but the moon has a lower density. The moon was primarily formed from mantle material, the outer layers of these objects. The cores, the metallic cores, weren't disrupted. The moon has very little in the way of volatile elements. This would have been vaporized in the impact because they have a low melting point or boiling point. They would have cooked off in this violent impact. And so not a lot of them would have ended up on the moon. And the isotope ratios in lunar and terrestrial rocks are quite similar. So the surface rocks have a common origin between the Earth and the moon. The multiple theories have been proposed to explain the origin of Earth's moon, and the currently accepted theory is the giant impact hypothesis that explains a number of the properties of the Earth-moon system. Yeah. Here I have some images of a simulation showing this process. So you have something like the size of Mars, strikes something the size of Earth, flings off material, a bunch of that stuff falls back to the Earth, a bunch of it flies off into, freedom, and some of it condenses to form the moon. So this is a computer model of that. So some history. About 4 billion years ago, the moon had lots of craters, but no Maria. By about 3 billion years ago, the Maria had formed, and now they're also covered with craters. And that finishes off chapters 8 and 9. The Earth and the moon in bulk, the tides. Yeah, we covered those. So the Earth structure from the inside out is the core, the mantle, the crust, the hydrosphere, the atmosphere, and the magnetosphere. The tides are caused by the gravitational effects of the moon and the sun. The atmosphere is mostly nitrogen and oxygen, and it thins rapidly with increasing altitude. The greenhouse effect keeps Earth warmer than it would be otherwise. We can study Earth's interior by studying seismic waves. The crust is made of plates that move independently. Movement of plate boundaries can cause earthquakes, volcanic activity, mountain ranges, and rifts. New crust is formed at rifts, shows evidence of magnetic field reversals. And the Earth's magnetic field traps charged particles from the solar wind. And the main surface features of the moon are the Maria and the highlands. The moon is heavily cratered. It has no atmosphere and a large day-night temperature variation. And tidal interactions are responsible for the fact that the only one side of the moon always faces the Earth, the synchronicity of the moon's orbit. And the moon's surface is both rocky and dusty material. There's evidence for ancient volcanic activity in the Mara, and there's also a few extinct volcanoes in places, generally in craters. The moon apparently formed as a result of a large object colliding with the Earth. So that's it for today. That was the end of chapters 8 and 9. I'm still grading all the homework and worksheets and stuff. The tests are all graded. I'm just finishing off the curve before I post your grades. Yeah. Any questions? There was something in the chat. So, have a nice day. I'm going to stop sharing. End the meeting.